voice from above.
So we'll wait until like 10 or something. I don't
No,
know.
not even that long, just like
Oh.
maybe one more minute.
Oh, okay.
Yeah.
We can wait a little longer. I don't know if that's gonna make any difference at this point, but.
We usually wait just till a few minutes after, just in case people are coming
Sure.
over from classes. Cause there's people, I know there's people on Zoom that have to get off at 1, so that's why.
Yeah, I don't foresee myself going that long, so. For some reason I cannot see, or maybe it's this over here. Let's see where is there a camera for the television that's pointing at me at all?
Yeah.
All right, that's fine.
Do you want me to show you where you are?
You're right. I'm curious, like if I wander over here, right, will I?
No, we can't see you if you interact with your slides. So that's you.
All right, so this is as far as I get. Okay. That's good. I like to wander some.
I looked, they used to be, I think sometimes they have tracking cameras, but I think they turned it off. So
These lights just randomly turn
keep going off. There must be some timer. All right, I think we'll go ahead and get started. Okay, welcome everyone. Let me stand over here and give it a little space. I got a cold. Welcome everyone to our very last seminar for the fall 2023 seminar series at CARE. Today, we are very honored to have Dr. Gabriel Venegas. Dr. Gabriel R. Venegas is an assistant professor in the Department of Civil and Environmental Engineering and Centers for Ocean Engineering, Ocean Acoustics Research, and Education, and Coastal and Ocean Mapping. He conducts research in the fields of underwater acoustics, acoustical oceanography, and plant and animal bioacoustics. Specific areas of interest include sediment acoustics in hydrodynamically and biologically dynamic environments, understanding the effect of organic carbon sequestration has on sediment geoacoustic properties, and the acoustic scattering from underwater flora and fauna. Dr. Venegas received his BS degree in mechanical engineering from Boston University. I did too, not mechanical engineering, but go be you.
No way.
Yeah, biology. And his PhD degree in mechanical engineering with a federation on physical acoustics from the University of Texas at Austin. He's a member of the Acoustical Society of America, the Coastal Estuarine Research Federation, and the American Geophysical Union. So with that, I will turn it over to Dr. Venegas.
All right. If you've read my title, it's a mouthful. So we're going to try and dissect that a little bit. So shear and Scholte wave measurements on surficial intertidal mudflat sediments using medical sonoelastography techniques. So this is a collaboration between UNH and the University of Pittsburgh. And we have to make a few amendments to the title because admittedly, I won't be talking about Scholte waves today. We'll talk about what they are anyway, just so you know, but we won't really be talking about them. And I have to put a little insert here and say preliminary. Whenever I signed up for this, I thought I was going to have a lot more to show than I did. But it's probably for the best because I'm probably going to use up the whole time anyway. So, all right. My collaborators, Yoswan Chow, she's a new PhD student over at University of Pittsburgh. Jane McHugh, she's an undergraduate in environmental engineering here at UNH. She's in the audience. Tan Kim and John M. Cormack are colleagues at the University of Pittsburgh, and they're both acousticians. Here's a little outline, talk about some motivations as to, first of all, what the heck does all those words in the title mean? Some experimental motivation, just general talk about sediment acoustics of mud and why we're interested in this. And then briefly talk about what medical sonoelastography is and why we're using it. We'll go into the methods of what we did for these measurements in these mudflats, talk about some results, and wrap up with discussions. So if you've taken my underwater acoustics class, you've probably seen these animations before. They were shamelessly taken from Dan Russell down there in the corner in that link. He has a lot of great animations. I'd recommend you check them out. But when we think of sound, we think of compressional waves right on the top left. So these are little particles, have some velocity and moving back and forth, and they're transmitting some kind of information or energy, the wave, right? There's also a shear wave, which the particle motions are traveling perpendicular to the direction that the wave is traveling, right? They're both bulk waves, so generally once they're out in the field, out in the far field, they travel as, they disperse as 1/r, right? So and generally shear waves are slower than compressional waves, and they propagate less effectively, particularly in marine sediments. They attenuate more than compressional waves. So here is an example of a surface wave. You can see the particle motions are elliptical. They're a little different than water waves in the sense that at a certain depth, the rotation of these particles change in direction. Well, water waves, they sort of both rotate in the same direction. And you commonly think of these when you think of an earthquake. So they spread as 1/√r, so they don't attenuate or they don't lose, local energy as easily, because they can propagate for longer distances at higher amplitudes. And these are the things that really cause a lot of damage when you think of earthquakes, because they can travel so far, high amplitudes. Well, a Scholte wave is basically the same thing as a Rayleigh wave. Instead of a free surface, though, we can approximate the Earth as the solid and the free surface as the air. But if you put some kind of fluid on it, like for example, water, it becomes a Scholte wave. And so these are slower than shear waves, but they propagate more effectively over long distances. And this sort of wave depends on shear modulus and Poisson's ratio. So how stiff the material is, so why do we care about these waves in sediments? The Navy certainly cares. They're mostly the sponsor of this work. So they're interested in the sense that where they have a source, it could be a ship, it could be another one of their submarines, and they're trying to transmit and see underwater very long distances, let's say 30 kilometers. So in the continental shelf, that depth is only 60 meters, right? So you have this aspect ratio that's impressively narrow. And so you're trying to see as far as possible. And to do that, you need to understand the boundary conditions, right? Because you can imagine how many times that sound is interacting with the boundary as it goes there and as it comes back. So therefore, they care about characterizing the bottom. And they care about it so much that they have this multi-year, multi-institutional field campaign that they funded called the Seabed Characterization Experiment. So I was a part of this throughout my graduate school, and when I came here as faculty, I also took part in it a few years ago. And so here's this New England mud patch. The objective is to characterize the acoustic properties of this New England mud patch using direct and inverse methods over a wide frequency range and spatial extent. And the idea is for these measurements to inform modeling efforts to how to understand how sound propagates in these finer grained sediments that they don't really understand at this point. So the mud patch, you can see, is just about 100 kilometers south of Martha's Vineyard. And here you see a mud thickness map. So the yellow represents thick mud, and the units are in two-way travel time in milliseconds. So it's just a huge patch of mud. The depth is very consistent, so it's a really great place to do controlled inferences, right? And it's accessible, so it's pretty close to Woods Hole. So what is mud, right? I mean, you probably know what it is. It's nasty. It smells bad. But there's so much more to this mud. It's basically everything. So sand's just in the beach, it's just sand, right? It's just grains. But in the water, it's just sand and water. Mud's a mixture of all these different things. So you have different sized grains. So you have sand and silt. And then you have these little electrostatically charged platelets called clay that are tiny. Less than 4 microns is generally what people think of as clay. So what is the New England mud patch? That's the ultimate question here. Here we have a figure adapted from this paper by Marion, and it's showing, for example, this could be silt and water, heat, and then it could be filled with various amounts of clays So you could have grains in contact, you could have still grains in contact with some clay inside, and then you could start to have this suspension of minerals, right? As it goes out. So there's a wonderful paper by a group in Japan that have a method to prepare water saturated muds and prepare it for scanning electron microscopy. And it's an impressive methodology that we actually will talk about, that we also basically followed their procedure and did the same thing with these mudflat sediments as a proof of concept for trying to do this with a seabed characterization experiment. And that's what we're going to talk about today. What they also did, which is extremely interesting, is they stained their samples with basically uranium. So it's uranyl acetate, okay? They stained them with a bunch of other things like osmium, which is pretty gnarly. It'll fix your eyeballs, glutaraldehyde, and uranyl acetate, so they were, kudos for them, for putting themselves at risk like that. But what that essentially does is it makes these organic particles really heavy in the eyes of the scanning electron microscope, and so they light up. So you see those fluffy layers on the outside. So inside that is a clay platelet. Around that are a bunch of organic material. Okay, just to put that out there. And so these organics have been shown to absorb onto clay surfaces. There's a lot on this slide, and it's kind of supposed to represent where we are in the field, where there's a lot here. We don't know which is the correct one, but I'll just go over a few of them that could be used to describe fine-grained sediments. The first one is a really well-known model called the viscous grain shearing model by Buckingham over at Scripps, Institute of Oceanography. And he basically describes grain-to-grain contacts, and these, as the bulk wave propagates through it, these little contacts start to stick and slip, right, due to these microasperities. And that roughness is kind of like a spring. Now there's some fluid in between that as the bulk wave moves through, it squeezes little bits of water through those microasperities. And that's kind of like some kind of loss, some viscous loss, like a dash plot. And this has been very successful in describing a wide range of sediments, right? But the question is, like, are these silt particles even touching? Remember, we're talking about that diagram where the clay could be in between the silt. And there's a whole other thing that haven't really spoke about, is the organic matter. Is that organic matter actually the thing that's suspending the particles, or is it this clay matrix? We're not really sure, to be honest. Then to move to the right there, we have the modified corrected Revel extended BO, the MCREV. This has been Dr. Chatiris's life work, and it's quite an impressive model, and it accounts for a lot of things that we think we should account for. So it's poroelastic, so that's where the BO comes from. So it means it's like an elastic solid with pore fluid inside. And the relative motion between the skeleton and the water is kind of what dictates a lot of these losses, and sound speed, essentially. And so then he added this to reduce the number of inputs, because there are a whole lot of them. He used these Revel equations. He corrected it for force chains. So if you think of like a piece of sediment, and if you push on one side of it, there'll be a path, a force chain that will reach the other side. Well, there are a whole bunch of these different force chains, and it's the addition of them that creates this sort of bulk wave property. And then modified to include creep, which is kind of like how sediment deforms over long periods of time. And he brings in a type of creep, which he calls squirt flow, which is these little pore fluid squirting mechanisms. I'm not going to go into it too much. Okay, but there it is. And what I really want to point out here, though, is that he introduces something that's quite interesting that we're going to briefly touch on at the end of the talk, or near the end of the talk. It's the fact that some of these pore fluids are free to move, and some are not. Some are trapped, some are free to move. And he has that built into the model. Usually, unfortunately, you can't measure those things. But with the methodology we're talking about today, we can actually directly measure those input parameters. That model, I believe, has 6 or 5 input parameters, all of which you kind of have to measure the acoustic property and fit the knobs to get those properties. So it's not really a predictive model, and neither is viscous grain shearing. There are a few of them that you can't really predict. And then finally, there's silt suspension, which is based on Stokes' theory of just a bunch of silt particles of various sizes moving. So the wave comes in, it starts to move these silt particles. There's some viscous drag on a sphere, being held together by some kind of viscous fluid. And it includes grain size distribution, which is really neat. You can do this for an arbitrary number of sized particles. Right. Takeaways from here. Could be any of these depictions. You saw there's these clay platelets and water going through them, and you see these grains with microspherulities, and it's sort of, they have to be touching, right? And then this one, these grains, they have to be sufficiently far apart. They can't be touching. So which is the right model? We don't know. We need to figure it out. And none of them account for organic matter. So here are some existing measurements and models in the New England mud patch. There's a pretty wide spread in the data, but these are all of the PIs that have contributed to this experiment. And the measurement that we're going to be talking about today, not for this seabed characterization experiment, but what we did for the mud patch or for the mudflats, is in the black square there. And the point I want to make here is that, and of course, we're going to be touching on this a lot. So these are compressional wave measurements. So this plot here is the sound speed ratio, which is the compressional wave speed normalized by the sound speed of the pore fluid. And on the right plot is the attenuation in decibels per meter per kilohertz. That's how we like to display this in the underwater acoustic community. Attenuation is just the loss of energy as the wave travels, intrinsic to the medium. So all of these potential loss mechanisms that we talked about in the models could be employed here. The point is, with these two wave parameters, you can fit 3 models. They'll give you some input they'll give you some inverted input parameters, and great. But you really need all 4 to sort of tease apart which model is correct. And then we also need direct observation of the microstructure to tease apart the models just in general, right? Because if the grains are touching, you can't use silt suspension. If the grains aren't touching, you can't use viscous grain shearing, And so new approaches are needed because these shear parameters are quite difficult to measure. So this is where medical sonoelastography comes in, right? And so they figured this out pretty early, and they did a really neat way of palpating tissue deep inside the body non-invasively. So what they do is they use this thing called acoustic radiation force, and it's essentially a transfer of momentum from the acoustic wave into the tissue. And it's proportional to the attenuation alpha, the instantaneous intensity, and the sound speed. And so what they do is they have this focused ultrasound beam, really high amplitudes. So high, in fact, that it literally pushes that tissue. And at that point, they can, I'm going to talk about this in the next slide, they can study the dynamics of these tissues for diagnostic purposes. So why would they care about that? For example, cancerous tissue is known to be stiffer than healthy tissue. So if you can probe something with a medical, grade ultrasound probe, and then listen to how that tissue moves. And I'll talk about how we actually listen for the movement of tissue. Then you can potentially see cancerous cells non-invasively without using any sort of weird X-ray, radiation type measurements. This can be just done with sound, with ultrasound. So this is the crux of this is how we're going to do it in this talk. But this came out, when did this come out? In 2004, but this was originally proposed in 1998. Verkov was the one that actually made it happen. So you push with acoustic radiation force. There's this wave that propagates out. So the compression of the wave goes too quickly, but then the shear wave that's a lot slower, you can actually image using some kind of Doppler processing. So you can pixel by pixel. So I'm not going to talk about Doppler too much because I think, Dr. Blanford talked really great about Doppler last time, so we'll glance over it. But essentially, you do some kind of beamforming, you do some kind of cross correlation or Doppler to image this particle motion, and you can see the wave propagate. And so, if you measure that shear speed, this is the shear wave propagating sort of spherically. If you measure the speed of that wave, you can diagnose how stiff that material is. There's another application that's really kind of cool. Is they did this supersonic shear wave imaging, which is essentially doing what we just talked about, but focusing at different points along the transducer probe, the ultrasound probe. And what it does is creates this mock cone. And what it does, it also creates basically a plane wave propagating outwards in all directions. So the same idea as this supersonic image you always see with a plane going through the mock cone. But we're doing this with shear waves. So it's a lot slower, obviously. So we're talking like the shear wave is 2 meters per second, but we're moving that little dot 6 meters per second. Wow. So pretty cool stuff. Tanter et al. In 2008, just 4 years after that paper, I think Tanter was also an author on the 2004 paper. They demonstrated that they could see large and small breast lesions using this shear wave elastography technique. So pretty cool stuff. We're going to use this for nothing. So here's our experimental sites. We wanted to pick something a little more accessible. And here's Dr. Peprocki and her student. And they'll let me tag along because these are actually their sites that they're using for another project, but we're sort of joining forces in these same sites to do all this different analyses. So you see, we have this site, this lab in UNH called the Jackson Stream Lab. So it's a wonderful place. It's beautiful. And you can see where it is, and it's in the Great Bay. The first site we're going to talk about is Woody. I didn't name these sites, but this one's called Woody. Okay, so or W. And here's a picture. We basically take a bunch of these planks and we bring them out into the sort of more centrally located part of this mudflat and take cores. So here's an example of the top view and side view of a core from Woody. You can see on the top core, there's quite a bit of like a mat, like a algal mat that's occurring on the top of that. And these cores were about 6 inches in diameter. The other side was closer to Adams Point, and it's basically kind of tucked in right in that corner there on the top left of that aerial view. And we basically just wait for the tide to go out, take your samples, and go back to the lab. So a lot easier. You don't have to go 100 kilometers offshore and pay a bunch of money. So using this to hash out our techniques. So here's the same top view and side view of a core. You can notice that, this one looks a little smoother on the side view than this one. Looks a little grittier. You can see a little worm burrow on the bottom there. So working with biologists, I've found that worms actually, they like some kind of mud that's got a little bit of grit to it. They don't like the really goopy stuff because they can't move. Anyway. So we took these cores back to the lab This is Carl. Carl stands for core and resonance logger. And we put the cores in Carl, and it essentially works using a function generator, right? And an amplifier that sends the signal to the source, travels through the core to the side of the core, gets received, preamplified, and read in the oscilloscope and digitized by the oscilloscope and saved to the laptop there. We performed signal tone bursts. So these are basically just little sine bursts in duration, short duration time bursts. And we decided the duration of that due to this wall bounce. So we wanted to make it short enough so that you could differentiate the wall bounce from the direct path. And generally each of these pulses has a bandwidth of about 60 kilohertz. So these are the signals we used. We calculate the velocity ratio or the sound speed ratio using this expression where CW is the sound speed of the water-filled core. Okay, so we have a reference core that we measure first, then we put the sediment core in there. ID is the inner diameter of the core, and delta T is just using a cross correlation in the time domain to figure out what that delay time is of these signals. So you'll see these signals here are the received signal through the water-filled core, just so it's clear what the signals look like. And then the attenuation is done in the frequency domain. So we take the Fourier transform of the received signal through water and the Fourier transform of the received signal through the sediment. We take their ratio, 20 log 10, 1 over the ID, and we pick the frequency of the center frequency in these tone bursts. So each of these signals, we would pick those values for the center frequency of the pulse. We did this other cool technique where we put out a really long chirp and compressed it. These are the compressed signals. The blue is through the water and the green, I think it's green, is through the sediment. And we shape them, and they go from 50 kilohertz to 1.5 megahertz. And we shape them to account for the, frequency response of the whole system. So we have a more uniform energy throughout the band that we're chirping through. So we take our velocity ratio in the frequency domain, and instead of delta T, now we have delta phi. And phi is the phase, or the angle, this little angle symbol is the phase of that ratio, right? And the attenuation is done the same way, but instead of doing it at one frequency, we're doing it at a whole bunch of frequencies. Which frequencies exactly are we using? So here's an example of the received signal. Blue is through the core, through the water-filled core, and red is through the sediment. And the bandwidth for either of those signals are pretty much an order of magnitude larger than the first case. So you send one long chirp and you get all that information instead of having to send all these different individual pulses. This is kind of a new technique for this system that I'm testing out in this talk. So moving on to other methods using elastography. So we first, I wanted to show you this method using a tissue phantom, which I learned is just gelatin. So 5% gelatin, 1% cellulose, and the phantom is sort of like a fake tissue. That's why they call it phantom. And it's this nice looking stuff right here. We used an ultrasound probe that we put in a glove. And we made sure that there was ultrasonic coupling channel between the glove and the sensor. We did this because we don't want to put this pretty expensive piece of equipment into salt water. So sure you it works just fine, and we'll see how it works in a second. There's some more information about the probe if you're interested. We do this autocorrelator to estimate Doppler shift and those particle velocity, which I won't talk about as to how, but this is the movie. So you send out that acoustic radiation force, pushes on this material, and then you literally are imaging the shear wave transmit. Right? Very cool. All right. This is the one mathy part of the talk. So if you've taken my underwater acoustics class, you know that you can describe the particle velocity using some displacement, right? Some amplitude and some phase, right? This looks familiar. Okay, so we're just gonna zoom here. It's a little different here. There's a case of S. That case of S is the shear wave number or shear wave vector. So this is the particle velocity. It's traveling in space and time. There's that phase in there in the corner. And this is kind of what we're after. We were interested in this wave vector field, K sub S. So it turns out if you take the amplitude of that, you get the component in the X direction, that way, and the Z direction, downwards. That amplitude is essentially the wave number, which is equal to 2 pi times the frequency over the shear speed. Right? Shear speed. That's what we're after. How do we get it from this material, from this experiment? So what we'll do is we'll take the Fourier transform of the particle velocity. Okay. This is an example of the real part of that Fourier transform at 200 hertz. We picked 200 hertz because there was a lot of energy there. That's why I picked it, but it's just a demonstration, right? So this is in the frequency domain at one frequency, and we do this Fourier transform at each pixel. We do each pixel, so it's kind of like the time is in the axis, right? And then you pick a point. In this case, it's the real part at 200 hertz. So you see all these wave propagation. So that U in the frequency domain, U of F, right, is this amplitude U naught of F with some phase e to the minus ks dotted with the right. So there's that case of S, right? So this is the real part. U naught is the amplitude. That part in the exponent is the phase. Right? So that's what we're after. If we take the phase and then take the gradient, so it's kind of like a derivative with respect to space, right? You get case of S. That makes sense? So we use this Stravinsky-Golay method to take the spatial gradient of this plot. Instead of this, instead of the real part, it will be the phase of that U. Okay. And then we use that amplitude of the gradient of the phase, okay, to get shear speed. Okay. So so what we do is we take these little boxes, right? The one moving to the right and moving to the left, moving to the right. Blue is leftward, or green is rightward. And we take some kind of window here and do that processing to find the shear speed. And we plot it. And we move it down as like a moving window almost to do the same processing as a function of depth. And we get propagation angle and shear speed as a function of depth in the fan. So you can see that the wave is sort of spherically moving. So there's positive direction above that focus and negative propagation angle below that surface, that focus. And you can see that the shear speed is more or less constant, which we expect for the fan. All right, next, we're going to take those samples after we've driven them all the way to Pittsburgh and driven them all the way back. We're going to get them prepared for microscopy. So I created this little 3D printed guillotine, essentially, to create very small, precise pucks of mud. And so these are just simple drinking straws. And the idea is you put the straw in the top of this guillotine, and then you take a little, X-Acto knife and put it, it's hard to see in this slide here, but you basically put it through and it creates a really small, 2 millimeter sized puck. So they're the pucks. We engulf them in agarose gel. Okay. Then here they are sitting in our first bath of what we call glutaraldehyde. So I mean my lovely student Jane, is basically putting them through all of these different processes to do two things: to stain the organics, but not with uranyl acetate. We're going to use uranolus, which is the non-radioactive version of this. Sweet. So we stain them with these things to kind of preserve the proteins and the carbohydrates, but also the osmium makes it a little heavier. Uranolus also makes it heavier, so it lights up in the SEM. And then what we'll do is we'll take a bunch of different sequentially more ethanol concentrated baths, right? So we basically put them in a little bit of water. So start off with a lot of water, a little bit of ethanol, and then we do the whole series until you get to 100% ethanol. What that does is essentially removes the pore fluid and replaces it with ethanol without changing the microstructure, according to this paper. And then what we'll do is we'll replace that with basically ether. Don't really know what it is other than you shouldn't breathe it in or drink it. So we were doing this, of course, all under the hood. And then you replace the ether with epoxy. So the ether is there so that the epoxy can go in to the pore spaces. And we're talking like really small pore spaces. And it worked. So I'll show you that it'll work. But we were a little skeptical, right? I mean, yeah. So we now have replaced the pore water with epoxy. And then you bake it. And so now you have these very stiff little pucks of mud, 2 millimeter slices that we can then look at in the X-ray microscopy. So X-ray computer tomography, which is here. So there's Jane, there's her back. She's putting the filter into the source. You can see essentially a puck of mud of epoxy with a bunch of these little subsamples inside. So that site was, I think, that was Woody, I think. And we're about to blast it with some electrons. And then we essentially polish using all these series grits of, geological grade polishers. And this is thanks to, Nick, what's his last name? Dickon? He's acknowledged at the end of the slide, so I forget which name. But he helped us with this. And you basically polish them very smooth, coat them with carbon, and put them in the scanning electron microscope. So some results, Carl measurements. I don't want to talk too much about this since the focus is sonoelastography, but they're quite different. So we have compressional wave velocity. So one is the same sound speed as water, essentially. At the low frequencies, they're both slower than water in mud, which is interesting, which is generally the case when you talk about fine-grained sediments. Adam's point has this, what we call dispersion, so frequency dependence, right? While Woody does not. Sort of remains more or less the same. And so the data points are the tone burst measurements, and the line is the chirp. So you get discrete frequency points for the tone burst and more or less continuous frequency for the chirp. And then here is compressional wave attenuation. And the other thing to note here is that you have a f to the 1 frequency dependence, and then below a certain amount, you have f to the 1.5. Anyway, if you're interested in sediment acoustics and loss mechanisms, this might be interesting to you, but otherwise not. And on the right, we have depth as profiles, essentially. You can see that they're relatively constant, where at 170 kilohertz, you've got faster sound speed and point than Woody, and more attenuation as well. All right, so here are the results this is the particle motion, particle velocity for Woody. So brace yourself, it's not going to be as clear as the tissue phantom, because that stuff is basically just gel and there are a bunch of grains in here. But you can see these waves propagate. Two things that strike me: you can't really see very deep, right? The issue with that is you're imaging this particle motion with a 5 megahertz probe. The attenuation at 5 megahertz in mud is astronomically high. So we're only getting a very small penetration depth. But nonetheless, you can still see waves propagating. It froze. So we do the same kind of processing. This is the real part of that frequency, the Fourier transform of the particle motion. And we see a depth profile. And in general, with the rightward and the leftward, you kind of see that there's the similar slant. There's some kind of spherical wave moving out. And then the shear speed shows values of between 1 to 2.5 meters per second, which is actually quite similar to the tissue, which is surprising. Now for Adams Point, this is a little grittier sediment. You still see the waves propagating, right? So with using similar analyses, you find, again, values between 1 to 2.5 meters per second. And you can see with at least the rightward propagating wave, there is kind of a very gradual gradient, which is kind of what you'd expect with viscous grain shearing when the grains are touching. Right. So now let's talk about the X-ray microscopy. This is for woody, a little puck centered at about 6 millimeters. So before we get started with the movie, we're going to have these regions of interest. The mineral you can kind of see is in gray. This green I'm going to call organoclay. Don't really know what it is because the resolution of this was about 3.5 microns, and clay is anything smaller than 4 microns. So we can really resolve the clay, to be honest. So we call this mystery gray area organoclay. I couldn't tell the difference because we stained the organic material with something heavier. So they could be very well the same. And the scanning electron microscope imagery will sort of clear that up. So you can see that most of it is this organoclay. 89.5% of woody is this mystery gray stuff. And then you have the pore water, which is blue. We'll talk about the grain size distribution after this. But if you peel away the organic clay, you see that there is pore fluid, that the connected pore fluid you start to drain out, and you see this trapped pore water, whereas most of the pore water is actually this trapped pore water, 0.6% as opposed to 1.87%. You can remove the minerals, and you see the trapped pore system. And if you bring the minerals back, you can see that all those particles were pretty much suspended by the green stuff, really. I mean, there was some trapped stuff that was within the green stuff, but the green stuff is generally suspending everything. Whether it's clay, whether it's organics, we don't know yet. And so here is Adams Point. So note the difference. Just look at the mineral. So in Adams Point, mineral is 27%. In woody, it's only, almost 6%. And this is of the volume. So you're generally getting a lot more minerals in Adams Point than in woody. And the other thing to note is organoclay is, 54%, still the majority, but 54%. And there's a lot more connected pore water than trapped pore water in this. So you can see 16% connected, 1.9%, 1.7% trapped. And you can see that when we peel away organics and drain the connected pore fluid. Work. There it is. Drain the connected pore fluid, you see there's a lot less pore fluid left, and there's so much more grain, right? I can show you the trapped pore water. We remove the minerals. You can see that they're still there, trapped by their organic clay, but not quite a lot. So we also use this, we took the minerals region of interest essentially, and we performed they call it a ferret diameter measurement, but it's sort of like your average diameter of a non-spherically shaped particle, okay? And I put it in units of phi, or capital phi. So back here I show phi is just this logarithmic quantity of the grain size. We do this so that we can see really, really small grains and really large grains kind of on the same plot, something we do a lot in underwater acoustics, but also in geology and geotechnical engineering, all that stuff. So you can see like where sand, silt, and clay is. So we're generally dealing with silty sediments. Here there's smaller silt particles than here. You can see that the peak is slightly lower. So a high phi means small grains. We're used to seeing this stuff all the time, so I forget to explain it. But a high phi is small grains. So Adams Point has a lower phi peak, which means it's coarser grains. So let's look, before I run out of time, at the backscatter. Anyway, this is a way of showing the bright materials are the hard stuff or the heavy stuff, compared like high electron density essentially, and the dark stuff are the lower electron density. So the epoxy in and of itself is dark, or was the pore water, and the light stuff is the grains and then potentially the clays. So we can zoom in. So this is a zoomed out sample. You see the bar here this here is 500 microns, right? Still pretty small, but we can go zoom in the 50 micron bar. We can still see this kind of stuff in the XRM, but we can then zoom in again, so you can see that there's these clear like silt particles. This is the surface that was polished off. You see the silt particles suspended in something. What is that something? You zoom in here between those two silt particles, and you see this bright stuff. And we found that there's a little bit of clay in there, but mostly it's this white speckle is stained organic matter. And you can detect this more quantitatively using EDS, or energy dispersive spectroscopy. So we take this backscatter image, and we can select little areas in there. And what happens is you can analyze the elemental composition of those areas. And so just to show you what a silt particle looks like, that's clearly a silt particle. It contains silica and aluminum. And there's no lanthanims, i.e. uranilus or osmium detected. And so what is the stuff suspended in? So we took that same process, but looked and selected area 4. And I apologize, this is hard to see, but what you're seeing is no aluminum peaks. And I show, in fact, it has this automatic detection system, and you can put in aluminum just to see, how certain is that from this measurement that there's aluminum present, which is in silt particles. And it says there's a 0% chance, 100% error that there's aluminum. So that's pretty definitive proof that in this case, in this specific area, there are very little silt or clay particles, mostly organic matter. So I don't know if I'll have time for discussions, but we can just have discussion. Maybe I'll open it up to everybody here. But basically, shear wave speeds are about the same, while the compressional wave speeds were starkly different, which is interesting in and of itself. The Woody and Adams Point sites were quite different. I'm estimating that the density of the Adams Point site is larger. And so to keep the shear speed the same, you would assume that the shear modulus, or G, is also larger. But we need to do much more analysis to figure this out. And the other interesting thing is that the majority of the volume is actually this organic material. And this could be controlling the shear wave speed. And so this suspension could be used with silt suspension theory. And so for some future work, we're going to do more analysis. investigate Scholte waves, which we didn't talk about today, redo some of this SEM stuff, and compare these measurements to the candidate models. So here's my acknowledgements. We have 5 minutes for questions.
Very cool interdisciplinary talk. I never thought I'd see a talk that has microscopy and acoustics all in one. I'm gonna kick off questions. I have a simple yet and probably naive question, but it has to do with Carl.
Okay. Carl's my baby, so
Baby Carl. So the outside part that you actually have like the mud core in,
yes.
what material is that made of and does it matter? Like, is that have any effect on the sound transmission? Can you comment on that?
It really does have an effect. And we negate that effect by measuring a reference core
Of the
with
water.
the same tube, but in a material that we know. So water. You can use any material you want.
So it doesn't matter what the material is,
It doesn't
really?
matter because it's a relative measure.
Okay.
Cool.
How long did it take you to develop Carl?
Various forms of Carl has been developed since 2016,
Okay.
but yeah, I think I had the first prototype made in like a couple months. Yeah, and it's like a simple thing where you use an Arduino to move a stepper motor so that these arms here, they actually move up and down so you can scan the core. And what took a while was actually the PowerPoint's kind of struggling here, but the challenging part was actually writing all of the software to control the oscilloscope, punch generator, and the stepper motor so that it would be sort of like a turnkey system with a GUI and all of that. So yeah, so we're using Carl for mostly sediments. We tried using it for sort of air saturated soils, but it's quite difficult to do that. But Carl's sitting in the lab right now, just waiting for his next core. Yeah. Any other questions?
I have another question.
Yeah.
Do you think you would, or have you ever detected any like marine fauna, so like animals living in the sediment with that
Using Carl?
method? But using Carl, or even just if you're trying to image the mudflat, like is that part of the goal as well, to look for any biological animals that might be there?
Yeah, so I'm interested in biologically active sediments. And so, yeah, I have a collaborator in Dauphin Island Sea Lab, Kelly Dorgan, who's a biologist, and we're constantly talking about how organisms like that screw up the scattering and propagation through sediments. So, yeah, I have a project.
Because you showed that image of the worm.
Oh, yeah.
Did you try to image it?
So
Do you have a video of what it looks like when the worm screws up your waves?
so the cool part about the second method of Carl, not the tone burst, but this is completely, screwed up. With the tone burst is that, with the chirps, is that when you compress it, you get this really narrow small time resolution, or I guess pulse. And so you might be able to see discrete scatterers in this mode better than the other mode. So that's kind of the first reason why, there's 2 reasons why I try to do this. One is that it's a lot faster. And then the second is that small time duration pulse, that once you compress this chirp, you get this nice narrow pulse. You might be able to see those discrete scatters.
So if there was like an object in your mud, would you be able to visualize it?
You could see the forward scatter from that mud.
I feel like that's like a really fun game that your lab should play, of like putting
Find the worm.
fake objects in the mud and having people trying to identify what it is.
Where's worm? Yeah.
Yeah.
We also have like a project using single beam echo sounders that are in the cloud at this point from the data. Invert properties from the field just to detect, like ecosystem, various properties about the ecosystem, for example, like volume fraction of burrowing and fauna or something.
Cool.
So, yeah, we'll see what that gets us. We'll see how much information we can get out of those data, but that's also the goal. System monitoring aspect.
Super cool. Are there other questions? Just asking all the questions.
Yeah, Gabe, with the 2 sites you had being exposed and probably biologically active, did you see trapped gas in the sediment? Or what effect would that have?
Yeah. It would certainly have a big effect. In fact, it would. Yeah, and that's something that we should look at too. I mean, the good part is we have the X-ray microscopy. And the way I threshold it, so the way this works, the way I made that pretty picture is that you have a bunch of gray values that the X-ray comes back. And it's sort of arbitrary as to where that threshold lies. And you sort of have to say, well, this is clearly a silt particle. So you sort of move that bar until you get all the silt and nothing else. But there's some really dark areas there that I just showed as pore fluid. But yeah, I've used this kind of methods to look at gas bearing sediments in seagrass meadows, for example. And we see quite a bit of grass, or quite a bit of air. But I didn't really see much air in this sample, to be honest. It's such fine grains, and you can see how much trapped pore fluid there is, that it doesn't really drain as much as you might think.
Okay.
Even though it is seeing the air twice a day. So yeah, it's a good point.
Well, with that, I hear the bells ringing. So we're out of time, but if anybody has questions for Dr. Venegas, you can ask him in the hall. I want to be respectful of whoever needs this room for a class if they need it. So thank you everyone online who joined us for the talk. And thank you everyone. Have a wonderful rest of your day. Let's give another round of applause.
Thanks, Gabe.